So welcome back. In our last lecture, we introduced the Laplace transform, something entirely new, the Laplace transform of a time domain function f. Of a real valued or complex valued even function from the non-negative real numbers to r or c. So we have the Laplace transform and we define this. And we define this like that. And then we use this definition to derive the Laplace transforms of 5 very common functions, the following. So 5 functions. Number 1 is the Laplace transform of 1. This means of f of t is equal to 1 for, and we found this to be 1 over s, and this is defined for all s which are complex numbers, and the real part of these complex numbers is required to be positive. If it is not positive, then this integral is not well defined. We then determine the Laplace transform of the Heaviside function. The Heaviside function is this function. It is 0 up to a time a, and then it goes to 1. It's like a switch that at a time a, it flips from the off position to the on position. And we found that the Laplace transform is a function of the complex variable s, with the real part of s being positive again, and the Laplace transform is exponential minus as over s. We also found the Laplace transform of the exponential function, which is a function of s. It is a complex function defined by 1 over s minus a, and s is a complex number with a real part of which is larger than a. Then we also found the Laplace transform of t, and we found this to be 1 over s squared. But we also found the Laplace transform of t squared, and we found this to be 2 over s to the third power. These are all defined for complex numbers s with a positive real part. And if you continue this procedure, you can find that the Laplace transform of t to the nu power is nu factorial divided by s to the nu plus 1 power. So we have, once again, constants, Heaviside function, exponential, polynomial type terms, t squared, t cubed, and so on. And last but not least, we determine the Laplace transform of sine and cosine. And we found that these two, we proved that this is like that using the exponential. Actually, we used the exponential to prove these two formulas using the extremely very useful identity that exponential of jz is equal to cosine of z plus j times sine of z. And this is extremely useful because it establishes a relationship between exponentials and sines and cosines. So whenever we find it difficult to work with sines and cosines, we can resort to exponentials, and vice versa if this is the case. So we used the exponential function to prove that the Laplace transforms of sine and cosine are like that. We didn't derive the domain of these Laplace transforms. Apparently it is some subspace of the complex numbers, some subset of the complex numbers. So it is, in fact, all those complex numbers with a positive real part. We didn't prove that, that was an exercise. If you're going to prove it, you have to prove this identity, not for a being a real number, but for a being a complex number. So we proved these identities. Now, especially in electrical engineering, we have two types of signals on top of these, which are very important. So the first type of signals is signals defined piecewise, and these are important because, for example, you might have an engineering system that behaves in a particular way, and then a switch flips, and then the system starts to behave in a different way. So we have a switch here, and the function now we say is defined piecewise. So in this part of time, piece number 1, in this first piece, it's defined like that. In this second piece of time, it's defined differently. So we're talking about functions in which switching phenomena occur. And number 2, periodic signals. These are also very important in engineering. We have seen a couple of periodic signals so far. So this is periodic, this is periodic. You have more interesting signals, like the square signal, for example, and so on and so forth. So it is important for us to be able to derive the Laplace transform of switching signals and periodic signals. In this lecture, we will focus here. Okay, so let us state the problem. What we're trying to do here is that we're trying to determine the Laplace transform of time domain functions which have this form. F of t is given by f1 between 0 and t0, sometime t0, and after this time t0, the function changes and goes to f2. An example of such a function we have encountered already is the Heaviside function, h t0 of t. This is a function which is equal to 0 for t between 0 and t0, and then 1. And of course we know the Laplace transform of this function. It is this function. Now there is a very interesting fact about this function ft, and this fact is that we can use the Heaviside function, which I'm repeating, we can think of this function as a switch that goes from 0 to 1. We can use this switch to turn it on when the function changes from f1 to f2. In other words, there is a way to write this function equivalently using the Heaviside function. I will give you the fact and then I will explain how it came about. So I can write this function f of t as f1 plus the difference f2 minus f1 times h with parameter t0 at time t. Why? And this is because here is our function ft. This term, this whole term, is equal to 0 if t is below t0. This is t0, alright? So before here, this whole second term is equal to 0. So function f is equal to f1. And after t0, this ht0 becomes equal to 1. So this is 1. And this is f1 plus f2 minus f1 is equal to f2. So this continues as f2 at time t. And this is the first very useful fact. And this is very useful because it allows us to do the following. To say that the Laplace of this function, f, is equal to the Laplace of the right-hand side, the Laplace of this function, f2 at t minus f1 at t, times h t0 at time t. Now, if we can determine the Laplace transform of f1 and the Laplace transform of this function here, then we have determined the Laplace transform of f. And there is a very useful theorem. And the theorem states the following. It says that if we have a function w for which we know the Laplace transform, then this holds. If we know the Laplace transform of w, we can find the Laplace transform of w at t minus t0 times the Heaviside function with parameter t0 at t. But what about the Laplace transform? Let's not call it w, let's say g of t times h. And I'm very sorry, but there is no result for this expression here. So unless you give me your function w in the form w of t minus t0, then we cannot have a result here. So if g of t is equal to some other function w of t minus t0, then we're fine, we can use that. Otherwise, we don't have a result available. Now the question is, how can we use this theorem over here? In other words, this f2 minus f1, can we write it as a function w of t minus t0? And if yes, how? And we are going to explore certain cases through examples. So let's see what we can do here. We have a function f of t, which is t for t between 0 and 1, and then this polynomial for t above 1. We know we can write this as follows. We know we can write this using the Heaviside function. So this is f1, this is f2, this is f1, this is f2. We know we can write that this is f1 plus f2 minus f1 times the Heaviside function with parameter 1. Now this is equal to t plus, let us simplify the expression in the parentheses. But this expression inside here, it's not a function of t minus 1. We would love it to be a function of t minus 1, because if it were, we would be able to use this expression but unfortunately it's not. So there is a little trick. When this function, let's give it a name, let's call it function g, for example, g of t. When this function g is a polynomial, we can use Taylor's approximation theorem. But how is this even remotely relevant to what we're trying to do here? We're not trying to approximate it, we're trying to write it as an expression that involves t minus 1. I mean, we would love to have something like this. Some number times t minus 1 squared. This 1 is the time instant where things change, plus some other number times t minus 1 plus some third number. So a polynomial again, but in terms of t minus 1, not in terms of t like this one. But the answer is, surprisingly, we can use Taylor's approximation theorem, which is, in this case, it becomes Taylor's quote-unquote approximation theorem. We don't have an approximation anymore. Let's see why. So we have g at t0, t0 is equal to 1 in this case. So this is how Taylor's approximation theorem starts. It goes g at 1 plus the derivative of g at 1 times t minus 1 plus 1/2 the second derivative at 1 times t minus 1 squared plus etc. Only that these etc. part involves the third derivative of g at 1, and then the fourth derivative of g at 1, and so on and so forth. But here we have a second order, this g is a second order polynomial. Therefore, you can verify that the third order derivative of the second order polynomial is equal to 0, the fourth order is equal to 0, and everything else is equal to 0. Therefore, we can write g of t like that without an approximation error. It is an exact derivation. But it makes sense, right? Because Taylor's theorem gives us the best polynomial of order 2, in our case, to approximate a polynomial. So when you approximate a polynomial by another polynomial, you get the original polynomial itself. So this is my function. Let's find the derivative of this function and the second derivative. And let's find the value of g at 1. So it is 1. The derivative at 1 and the second derivative at 1. And let us now apply Taylor's approximation. We will simply plug in these values inside here, and we have so we have 1 plus 10 times t minus 1 plus 3 t minus 1 squared. So let's write it here. So this function f of t is t plus, and then this expression g of t, which is therefore, what is our function w in this case? Well, w, let's call it w of t, is 1 plus 10t plus 3t squared. And in fact, this expression here is nothing but w evaluated at t minus 1. And we know how to determine the Laplace transform of w. Let's make some space on the whiteboard. So very good. We have used Taylor's approximation theorem to write this function, which we called g of t, to write it in this form with Taylor's approximation theorem. And we can now derive the Laplace transform of function f of t, which we have written like that. So the Laplace transform of f is the Laplace transform of this expression. So the Laplace transform of t plus the transform of this whole big thing over here. So 1 plus 10 t minus 1 plus 3 t minus 1 squared. And we said that w of t is this function, w of t. Now if we use, first of all, what is the Laplace of t? We know that very well. It is 1 over s squared, defined for all complex numbers s with a positive real part. What is the Laplace transform of w? Let's write this here as a note. So the Laplace of w is Laplace of 1, so this is 1 over s, plus the Laplace of 10 times t, so 10 divided by s squared, plus 3 times 2 divided by s to the third power, and 3 times 2 is 6. So this is the Laplace of w. And we know this from the theorem that we stated before. Now this gives us the final result. So the Laplace of f is given by 1 over s squared plus, and now this expression has the Laplace transform, because of this theorem, e to the minus 1s, 1 is t0, times the Laplace transform of W. And that's it, really, that's it. So what did we do? We took this function f, which is defined by, it is defined piecewise. It has two branches. It is defined by t for times below 1 and by this polynomial for higher times after 1. We wrote it equivalently using the Heaviside function. Then we determined the polynomial here. We identified that this is a polynomial, and we used Taylor's approximation theorem to write it in terms of t minus 1, t minus this time over here, the time where the function changes definition. From f1 it changes to f2. So we were able to write this function as a function of t minus 1, and we did it like that using Taylor's approximation theorem. And then we came here and we applied the Laplace transform on the sums we have here on the right hand side. So the Laplace transform of t plus the Laplace transform of this expression. And then we use this theorem to derive the final result. So pretty much this is it. You can do one of this type. You can try to solve an exercise like that. So take this function f, which is given by this polynomial for t between 0 and 5, and this other polynomial of degree 4 for t above 5. And the exercise is determine the Laplace transform of this function. And exercise number 2, nothing stops us from doing functions, from determining the Laplace transform of functions with multiple branches. So here we have a function defined in 3 separate pieces. So from 0 to 1, from 1 to 3, and from 3 up to infinity. So what is the Laplace transform of this function? Of course, what you need to do here is to find a way. It is not much different from what we have to do for functions with 2 branches. So find a way to write this function f of t as an expression that involves somehow h1 and h3. Perhaps try to do a little sketch to figure out how to write f in terms of h1 and h3. For both these exercises, use the expression use this theorem. We didn't give a proof of this theorem, but you can find the proof in the lecture notes. If you're interested in how you can prove this result, you can check out in the lecture notes, although it is very, very simple. So this much for today, and we will come back in the next lecture to complete our discussion on the Laplace transform and give some very important properties that will be very useful in practice, as well as talk about the Laplace transform of periodic functions that we encounter very frequently in practice. So thank you very much for watching, and until next time, goodbye.